Hello and welcome back. It's now time to work on another free body diagram example to get some more practice doing this crucial step in solving physics motion problems. Let's now take the example of a box that's sliding to the right on a horizontal floor and slowing down due to the force of friction. So here's a picture of the situation. I've got a horizontal floor that's kind of rough because the box is slowing down due to friction. And here's a box that's sitting on it and sliding on it to the right and slowing down as it goes along. Before we get to the free body diagram, it's helpful to draw a motion diagram so that we know the direction of velocity and acceleration, which are useful in interpreting the forces shown in the free body diagram. So here's a motion diagram of this box. I show the object as a dot and I show velocity vectors as they appear over time. At first, the box is moving to the right at a fast speed, and then as time goes on, it's slowing down and then slowing down some more and so on. So here are my velocities. An object that's moving to the right and slowing down has an acceleration that points to the left. We have discussed this before, but let me just remind you that there are a couple of ways of doing that. We can think about the definition of acceleration, which is final velocity minus initial velocity divided by time duration. And in this case, final velocity is here. To subtract the initial velocity, I got to flip it and then move its tail to the tip of the final velocity, and the resultant vector will point left. And when I divide that by the time duration, the direction does not change because time duration is a positive scalar, so that tells us that the acceleration will point left. Another way is that we have seen before that when an object is slowing down, the direction of acceleration is opposite the direction of motion or direction of velocity, which also tells us that the object is accelerating to the left. We'll keep this in mind as we develop the free body diagram of this object. Okay, so that's my situation. And now in order to draw the free body diagram, we got to start with drawing our closed loop around our object. So let's get started with that. And then we're ready to identify the forces that are acting on this object. I'm going to start here at the top and go around until I meet my first couple of forces as I hit this interaction surface between the box and the floor. So I've got a normal force that points perpendicular to the surface, and it's a supporting force. So for a horizontal floor, it's going to be pointing straight up like that. And then I got the force of friction, which I'll label F, which is from the interaction of the two surfaces. And since this object is moving to the right and friction opposes motion, the direction of the frictional force is going to be to the left. Remember, friction is parallel to the surface, so being a horizontal floor, this friction is going to be horizontal as well. And then that brings me to this point in the loop, and as I go around some more, there is no other force. Unless the problem explicitly tells us to consider air drag, we will ignore it for most problems in this course. So even though the box is coming across some air drag here as it moves to the right, we will ignore it because the problem did not specify it. Okay, those are my only two contact forces. And as usual, I have weight that acts straight down. Okay, that's my inventory of the forces acting on this box. And right away, you might be surprised about something here. The box is moving to the right, and the only forces that are acting on it are in the up, down, and left direction. There is no force acting on the box towards the right. So how is it moving? This is one of those intuitive things that we need to take some time to work out and reconcile with our common sense notions. The box presumably started moving because somebody pushed it in the right direction, and so there was a force applied for a period of time in the right direction which caused it to accelerate in the right direction. But then the pushing force was removed, and then the box was sliding on its own accord, but slowing down because of friction. As we saw in our motion diagram, the box moving to the right and slowing down implies an acceleration to the left. And according to Newton's second law, if I have F equals ma, and if I know that the acceleration points to the left, the net force on the box must also point to the left, which is what we have here. So the box does not require a force to be applied on it to keep moving to the right. That's what it'll be doing once it got started. If there was no friction, this box would be moving to the right at a constant speed forever, according to Newton's first law. In order to slow it down and bring it to a stop eventually, the force of friction acts to the left, which results in an acceleration to the left, which results in the velocity slowing down and the box eventually coming to a stop. Okay, so now let's draw the free body diagram of this object. As mentioned before, the free body diagram starts with a representation of the box as a particle, and then I start showing my forces acting on it. The box is accelerating in the horizontal direction, but it's not moving or accelerating in the vertical direction. So the two forces in the vertical direction must cancel each other. So whatever length I use for the normal force pointing up must be the same length I use for the weight pointing down. That'll give me a net force of 0 in the vertical direction, which is consistent with no change in motion in the vertical direction. And then in the horizontal direction, I've got the single force of friction that points to the left, corresponding to the fact that it's slowing down and accelerating to the left. So that's it. That's my free body diagram, and we're done. But let's take this opportunity now to introduce the concept of coordinate axes in solving these problems. So a situation like this where I got forces both in vertical and in horizontal directions, it's best to define our coordinate system. And your textbook shows the coordinate system with the particle at the origin. But if I draw the axes starting here, you might get those mixed up with the existing lines of forces. So I prefer to show the coordinate system off to the side and say that for this problem, my x-axis is horizontal and my y-axis is vertical. And we'll just assume that the origin there lies on top of the object here. So it's best to analyze problems like this independently along the two axes. Because the x-axis and y-axis are perpendicular to each other, motion along one axis does not affect motion along another axis, which is what allows us to consider them independent of each other. So along the y-axis, let me start with that first. I've got net force along the y-axis of the normal force plus the weight, and when I add them as vectors, given the fact that they are opposite in direction but equal in magnitude, I get simply a 0, which corresponds to 0 acceleration in the y direction. And along the x-axis, I've got the net force as simply the only force that's acting in the x direction, which is this force of friction, which acts to the left, which results in the acceleration to the left. So if you want to think about it this way, you could say that along the y-axis, the object is in equilibrium. There is no net force, so there's no change in motion. Whereas along the x-axis, I've got Newton's second law applying because I have a net force acting, which results in a net acceleration. So hopefully this example gave you some additional practice with free body diagrams, but also reviewed a couple of other concepts. We revisited the misconception that leads us to believe that simply because a box is moving to the right, it must have a force to the right applied on it. In this case, the box was moving to the right, but the force was acting to the left. And secondly, we reviewed the concept that acceleration points opposite the direction of velocity or motion when the object is slowing down.